Here's example 1. We have an object moving forward, and there'll be a force of friction going backwards. And the force of friction is just due to a rough surface. And we don't normally use forces in Chapter 2. It's supposed to be about kinematics. But we already know something about this from last year, so we're going to work them together. So if we say the net force equals the mass times the acceleration, we can say that the frictional force is the net force, which is negative mu k Fn. Negative because it's in the opposite direction of the velocity. And since it's on a horizontal surface, the normal force is simply mg. We can see that the masses cancel out and our acceleration is constant. So given this constant acceleration, you should be able to make graphs of position, velocity, and acceleration versus time, and state equations for each one. Well, obviously the acceleration is that constant. Since it's constant, we know the velocity is going to be acceleration times time plus the initial velocity, and you can put that in there if you'd like. And the position will be given by 1/2 at squared plus vit. Of course, the acceleration is negative. We can just assume the initial position is 0. It wouldn't really matter. And the graph should be a constant acceleration, but negative. The velocity has to start with a positive value. And due to the constant negative acceleration, it should be a straight line. If we assume the initial position is 0, then that's where we should be. We have an initial velocity, so that should be a slope positive, meaning we're going forward. But we're slowing down and coming to a stop, which means the slope has to approach 0. At that point, the object is stopped. The position will no longer change. The velocity is 0, and the acceleration is 0. You can think about why this happens simply thinking about friction. When the object comes to a stop, the friction stops too. There is no friction if it's not moving. So I wrote a little simulation to demonstrate this, and it's based on the idea of numerical integration. First here, I'm calculating the acceleration based on the drag force, and if there was a force pushing on the object in addition to that, which in this case is not, and we calculate the acceleration, and we can see the same old routine. The change in velocity we are assuming is constant acceleration for a small interval of time. We sum up our velocities, and then we use that velocity to calculate a small change in position, and then we sum up our positions, and then we plot the motion of the object. So before we run the simulation, I will tell you that we have an initial velocity of 7 meters per second. The initial position is at negative 6 meters. I've got a mass of 2 kilograms. And in this case, we're going to see a kinetic coefficient of friction of 0.25. So you would actually be able to predict where this object is going to come to a stop. So let's run the program and see what we get. Here's the object at negative 6 meters. And we're ready to do the graphs as well. And these graphs agree with what we just saw on the whiteboard. The velocity is starting out at a positive value, drops to 0. The acceleration is a constant negative value. And the position is moving forward and eventually slows to come to a stop. We have 0 slope for the rest of the problem. The acceleration is 0. And it looks like we're coming to a stop somewhere about 4 meters. Well, in example 1, the drag was independent of the velocity. The acceleration was constant. In example 2, we'll say the drag is proportional to the velocity. Of course, the net force is still going to be equal to ma. I should really label the box with a mass of m. And the net force is due to this drag, which is negative bv. So now we can see that the acceleration is going to change, not as a function of time per se, but as a function of the velocity. So this makes the problem a good bit harder. Again, we have to make graphs of position, velocity, and acceleration versus time. Now remember, that's velocity. We need to get an equation then with time in there, so we can check the idea of our graphs with the equations. Well, we can write acceleration as dv over dt, bring over the dt, and we would like to be able to just integrate this and get the velocity, but the trouble over here is velocity is a variable, and that is an increment. They do not agree. The increment that goes with the variable are on opposite sides. We have to get them together. I'll bring the velocity over and move the constants. Now I can integrate both sides of the equation, which will get me a time on this side. And knowing the integral of 1 over v dv is the natural log of v, I now have an equation that tells me something about my time and my velocity, but I need to put in the limits for this equation because we're starting with a certain velocity. If we don't start with a velocity, the problem will not continue because the object won't be moving and there'll be no drag. Plugging in our limits, we have the natural log of the velocity minus the natural log of the initial velocity, which is the same thing as dividing. And now we have to eliminate the natural log so we can solve for the velocity. I'll bring the constants over, use e as a base, which cancels out the natural log. And this will give me a formula for velocity as a function of time. You might recognize this as exponential decay. So what does that graph look like? Put 0 in for t in your calculator. You'll find out that e to the 0 is a 1, and your velocity at time 0 will be your initial velocity. It's a positive value. Okay, I'm using v0 here, and I was vi there. I'm making that a v0. Now, as time goes on, that number will get smaller. Now, it's not going to be a straight line. It's actually going to start to curve. Take a look at your acceleration. The slower we go, the smaller the acceleration. That would mean the smaller the slope. So it starts to approach 0. Now the question is, what is acceleration versus time? Now remember, that's not acceleration versus time. That's acceleration as a function of velocity. So we would want to take the derivative of this to get the acceleration as a function of time. The derivative of e to the x is simply e to the x, but we have to bring down constant in front of the t. Now, if you didn't want to take the derivative, we can substitute this equation in for velocity. Just doing the algebra, we get negative m over b times a for velocity. When we bring these constants over to here, we end up with the same equation for acceleration. Now, take a look at that negative sign. What does that tell us about the acceleration? It should be negative, because if the velocity is forward, the friction's backwards, the acceleration is negative, and so we start off down here. Again, if you plug 0 in for t, all of this becomes a 1, and now we have a value for our acceleration at time 0. And as t gets bigger, this term gets smaller. And the acceleration approaches 0 as well. And that agrees with the shape of this curve. The tangent lines are getting closer and closer to a slope of 0. Well, we have our velocity and our acceleration versus time. Now all we need is our position versus time. That's going to be finding the area under this graph. We can rewrite velocity as dx over dt. Bring the dt over. And now I'm going to take a moment just to make sure we understand where this is on this graph. This is the velocity at any given moment in time. And that's the y value on the graph. If I multiply by dt, then the area is my dx. So we want to integrate all the dx's to see how far we've gone as a function of time. Well, this is a little bit tricky. The integral of e to the x is also e to the x, but we have to be careful about the constants up there. We have to bring them down and out in front in inverse order so that you can check this with a derivative and end up with the same function that you started with. That has to be there. Now, either we add a constant or we plug in limits. I'm doing limits. First, we put in the upper limit, and then we subtract the lower limit, which is 0. Well, e to the 0 is going to be a 1, which reduces to m over b v0, and that's a negative. Well, that negative and that negative, which becomes a positive value. So this should be our equation for position as a function of time. Now, whenever we come up with an equation, we like to test it at extremes. So let's just see what happens to this equation if we plug in a 0 for this. e to the 0 is going to be a 1. And we're going to have a negative m over b v naught plus a positive m over b v naught, which is going to cancel out, leave us with 0. And that is exactly what we should have here. We will assume the initial position is 0. Well, as time goes on, t is going to get bigger, and this term is going to become smaller and smaller. As t approaches infinity, this term approaches 0, and we'll be left with this final position. So we know we're going forward, but the slope has to start to become more shallow. It will eventually flatten out, but it'll never quite reach 0 slope. 0 slope will be approached as time approaches infinity. Where is this term on the graph? It's the maximum position. We're getting closer and closer to it, but we never quite get there. What does this mean for the area under this graph? This graph goes on forever and ever, but the area is finite. Well, now we have all three graphs and we have all three equations. Now, believe me, this last one was a doozy, and that's really a level 3 plus problem in the Tipler book at this level in chapter 2. Certainly, we're not expecting everybody to do the calculus for all of this, but the sketch of the graphs seem reasonable, and if you do them approximately, you should be okay. Of course, we don't have to do any calculus. We could just use the computer simulation. Set the mass to be equal to 2 kilograms, let's say. And down here, I have a constant of b equal to 1.5. And down here is where I determine the acceleration. Well, that has to do with the drag force. There is no other force. That's a 0. So I have the drag force divided by the mass to get the acceleration. Well, how do I know what the drag force is? I have to go down to a subroutine where I calculate the force of friction. And here's that subroutine. So I'm down here calculating the force of friction. It's negative the direction of the velocity. And there's the constant b times v. So all of this is inside the loop. And we calculate the force of friction, calculate the acceleration, and then from there we can calculate the change in velocity and the change in position and sum them up. Let's take a look and see what the graphs look like. As in the last example, the yellow is the acceleration. There was a negative acceleration. It's approaching 0. The velocity is dropping off and approaching 0. But because that is an inverse function, the position graph does level off. We are only going to go this far. We're never really going to get to a final position. We approach it. It will take forever to get there, but we will never exceed that position. And that's what we're seeing here as this thing levels off. Now we'll go to example 3. And this model will tell us that the drag force is proportional to the velocity squared. Again, of course, the net force is equal to mass times acceleration. The net force is simply the drag. And now, again, we can see the acceleration is somehow proportional to the velocity. It's not to time. So we'll just keep our equation up here. Rewrite acceleration as change in velocity over the change in time. Rearranging. Take the integral of both sides. We can now relate velocity and time. No need for any special tricks. We know that the velocity to the -2 has to be raised by +1, and multiplying by the reciprocal of the new exponent cancels out the negative sign. And now I'll put in my limits, arriving at this equation, but I want to solve for v. Well, we've got to do some algebra. And now we can rewrite this. And now we have a velocity as a function of the time. Let's test this at extremes. When the time is 0, this term becomes 0, and we're left with a velocity that's equal to the initial velocity. As time gets larger and larger, this term will dominate. That will become insignificant. And as this gets bigger and bigger, this term will go to 0. So again, we're expecting the velocity to drop off. And to get the acceleration versus time graph, We can rewrite the velocity, and now we can take the derivative of this function. We'll take the derivative of the outside, bring the negative down, subtract 1 from the exponent, and then multiply by the derivative of the inside. So we do have an acceleration that is negative. And if t is equal to 0, we have an initial acceleration, and if we simplify, we get an equation that agrees with our acceleration equation as a function of velocity. And if t approaches infinity, the acceleration will approach 0 as well. So our graph starts at an initial negative acceleration and approaches 0. So we now have our velocity equation, we have our acceleration equation, we need to get our position equation. We'll work with the integral of the velocity. So we break that up into dx over dt, bring the dt over, take the integral of both sides. We can then use Udu substitution. We'll say u is equal to b over mt plus 1 over v naught. Du dt is b over m, which allows me to say dt is equal to m over b du. If I let u equal this term, then I can say the integral of u to the minus 1, but I want to get rid of the dt, so I will have to substitute. So my increment agrees with the variable. We have m over b, natural log of u, where u is b over m times t plus 1 over v naught. And now we should put in the limits from time 0 up to a final time, which works out to this expression. We can simplify that further, arriving at this final equation. And we're going to test this at extremes. If t is 0, then we have a 1. The natural log of 1 is 0, and yeah, we thought that the initial position would be 0. That worked. And as time goes on and on, this number will approach infinity. And the natural log of larger and larger numbers is still going to be a larger number. This thing is not going to approach a finite final position. So now we have everything in order. We have the position, velocity, acceleration. We have the graphs. We now have to complete a sketch of the position versus time graph. At time equals 0, we just said x will be 0. And we know it's going forward with a slope equal to the initial velocity. But as time goes on and gets larger and larger, the position will keep on increasing, even if it does so at a slower rate. Now, back in my computer simulation, I'm going to change this flag to indicate that we're doing a different type of friction. I'm using this value for my B. And down here where I calculate the friction, I'm now using that value for B times V squared. And it all comes back to doing the same little numerical integration techniques. We're calculating the force of friction, getting the acceleration, and then assuming the acceleration is constant for a short interval, and you know the rest of the story. Now look at that. Look at the position graph. It doesn't look like it's going to quite level off. It's leveling off, but at an ever slower rate. The object's going to go right off the screen. This matches the calculus. Well, you can take it a step further. If you know the initial velocity, and you know the mass is 2 kilograms, and you know we're using a constant of 0.4, then you could go ahead and predict the position as a function of time. The data is given up here, as well as the x position down here. So you can use this data to test your calculus. Just remember, we're not using the mu k. That was for a previous problem. That's not applying here. Well, if all of this seems extremely difficult, it is. This is as hard as it's going to get. You don't need to know how to do all of this stuff with the calculus, certainly at this point for sure. Just make sure you can sketch the graphs appropriately. And honestly, the numerical integration techniques using Quick Basic, That shouldn't be too bad, especially if you don't need to make it look really pretty. You can still get your answers numerically.